We have introduced two extreme cases for variable demand. First case, when the rent cost is far larger than the inventory waiting cost. And then the second case, we have the inventory waiting cost far larger than the rent cost. So in the first case, we will use analytical method to solve it because we can ignore the impact of the shaded area between the cumulative curves. So we can guess the expression. The optimum number of dispatches should be equal to square root of the rent cost times Tmax times d Tmax, and then it's divided by holding cost. And then on the other hand, when we have the inventory waiting cost is far larger than the rent cost, we need to use a shooting method. So today, let's look at some specific examples about how we apply our method. So here, let's consider a specific example where we have a time-varying demand, dt over t, and then the maximum time is 3. And then the cumulative demand curve have 3 pieces. In the first piece, the gradient is 100. In the second piece, the gradient is 80. In the third case, the gradient is 50. Okay, and then we have the parameter settings. Our rent cost is 10. Our stopping cost still 150. Our mileage cost 3. Our distance 13. So similarly, we can have our fixed cost to be stopping cost plus mileage cost 189. So let's solve this problem in different cases. First, let's consider the case when we have the rent cost is significantly than the waiting cost. So to apply our formula, we only need to know what is d Tmax. So we can derive the expression for dt based on the 3 pieces. If we write the 3 pieces rigorously, we can have this expression. So let's see the first piece. So when t is greater than 0 and smaller than 1, the gradient is 100. So we immediately have dt equals to 100 and t. So in the second piece, when t is greater than 1 and smaller than 2, this is a line segment. To express this line segment, we know that its gradient is 80. We can have the expression as dt minus d1 divided by t minus 1. And this is a gradient, which is 80. So this gives us dt equals to d1 plus 80 t minus 1. And then from the first case, we know that d1 is 100t. So this gives us 100 plus 80 t minus 1 gives us 80t plus 20. Now let's see, this is the third case. When t is greater than 2 and smaller than 3, we have dt minus d2 divided by t minus 2 equals to 50. So this gives us dt equals to d2 plus 50 t minus 2. Plug in the value of 2 in the previous case, we can get 80 times 2 plus 20 plus 50 t minus 2. This gave us 80 plus 50t. So with all this value, we can get d Tmax, which is d3 equals to 230. So in this case, we know this is 230. So we can plug in our formula. So this is equals to, and this gives us, so this is around 6. So in this end, we will have 6 dispatches. And then our load should be, so this equals to And also, we can try to estimate the average headway, because the headways can be different, right? So we can estimate our average headway. Average headway should be Tmax divided by number of dispatches. So now let's consider the second case. So when the inventory waiting cost is far larger than the run cost, to capture this, we fix this number to be inventory waiting cost. So remember the concept of the shooting method. So we'll first choose a time point for dispatches. For example, let's choose T1 equals to 0.7. We know like T0 should be 0 starting from the beginning. So recall our shooting method logic. So if we have T1 selected, we will get the gradient. And then the next dispatch will be determined by a parallel line with the intersection at T1. Then this gave us the next dispatch T2. So let's try to calculate. And there's a special case, what is T2? T1 is here. So the gradient at T1 is 100. So if we draw a parallel line, the parallel line, the gradient should be also 100. And then we find the intersection at T1 with this parallel line, we will find T2. So to get this specific value, we take a look at this part. So this line length is 0.7. And then we know this gradient is 100. So we can know the length of this line should be 70. Length of this first segment is also 70. So that indicates this value should be 140. Remember our D1 and D2 point. So D1 is 100. T2 is 180, so we can try to find the value of T2. In the second piece, dt equals to 80t plus 20 as we derived. So we plug in this value, this can give us 1.5. Okay, and then we can consider the next jump. In the next jump, remember this is 140, this is 0.7, so this point is 0.7, 140, and then we need to draw a parallel line with gradient 80, and then find the intersection here. So similarly, we can calculate the length. This is 0.8, and then the gradient is 80, so this length 64. So we have this point to be 1.5 and 204. And then we can try to find next t. In fact, we know d2 equals to and d3 equals to, so 204. That's in D2 to D3. So we plug in the form for the third piece, 80 plus 50t. So hence we have 2.48. So now we know T1, T2, T3. So now if we project T4, we need to do a parallel line and then find the intersection. So we know this line's 0.98 and this gradient is 50. So we know this length is 49. So we can further get this point to be, so we know like this is already greater than dt max, which is 230. So there will be no T4. So when you do the shooting method, if finally you cannot close this dispatch schedule, which means you could not reach the Tmax point, we can simply truncate it. For example, we can just last shipment ship the rest of the demand. So in this case, we can have 3 point, and then we have 1, 2, 3, 4 shipments. And the total holding cost can be estimated by the area times CI. We have obtained all the critical points. Now let's calculate how large is this total area. So here we have 4 shaded region. Let's see, this is 1, this is 2, this is 3, and then the last one is 4. So let's calculate them one by one. So for the first one, this is very easy. It's a pure triangle. From the point we can see the area should be 70 times 0.7 times 0.5. So this gave us 24.5. And then let's see the second area. The second shaded area is a concave triangle. So we can try to decompose it into 2 parts. The left one is a trapezoid. The right one is a small triangle. From the points, we can obtain the edge for this one is 70. For the middle one is 40. And then the edge for the top 0.7 and 0.5. Therefore, we can calculate the area. So for this one is equals to 70, 40 times 0.3. This gave us 16.5. And then the other small triangle gave us 40 times 0.5 divided by 2 gave us 10. So similarly, we can calculate the concave triangle for 3. Then for this case, we have the edge 64, 24, 0.5, and 0.48. So we can calculate this A, B. So the first one should be 64. So this equals to 22. And then the second one equals this area equals to 5.76. And then for the last triangle, it's a pure triangle. And then we can guess the edges 26 and 0.52. So this gives us the area to be 6.76. Therefore, if we add the total area, so this shaded area be 1 plus 2a plus 2b plus 3a plus 3b plus 4. This equals to 85.52. Okay, so recall that we have our total cost equals to holding cost plus the transportation cost. So now we have the total holding cost to be the shaded area times CI. And CI equals to 10. This gave us this amount of cost. And as for the transportation cost, we only need to consider the fixed cost because the variable cost does not change based on our schedule. So the total transportation cost, we have 4 shipments, and then each time the fixed cost is 189. Therefore, we can have our total cost equals to 1,611.2. So we have finished the one calculation for case 2 when the inventory waiting cost is far larger than the rent cost. So in this calculation, the total cost is affected by 2 parameters. One is the shooting method starting point, which is T1, and also the number of shipments. So finally, to really solve this problem, find the optimum cost, we need to find the minimum total cost for each T1. So this is a pretty hard task. So typically what we should do is that we will try to enumerate the value of n from 1, 2, 3 until a very large number when the fixed cost dramatically dominates. Let's see, for example, 10. And then we starting to search the possible T1 for each n, given the number of jumps. And then after we determine T1, and then we jump several times based on the number of n, and then remember the last shipments will cover all the rest of the amounts to Tmax, and then the number of shipments, 1, 2, 3, equals to n. So this is a framework to solve the second case.